welcome to CEC lectures. Myself Dr. Preeti Jagwani. I am Associate Professor, Department of Computer Science, Aryabhat College, University of Delhi. So from today we are going to begin a new series which is Advanced Data Structures and Algorithms, and in this series we will be looking into some specific data structures which are used for specialized kind of applications and scenarios, and also some algorithm which which are I can say designated under not under the basic algorithm but under the advanced algorithm topic. With this let me begin with the series, and the today's topic which we are going to study is skip list. So when we say skip list, and or particularly when we say we are talking about a list. So what is going to be the background behind this, or why this skip list is needed? What is this skip list? Let us try to see. Now I am sure that you all are aware with the data structures which is binary search trees, and the binary search tree is something which kind of you have a root element, and all the elements which are less than the root element comes under the left side, and all the elements which are greater than the root element are on the right side, right subtree, I can say. And what is the biggest advantage of the binary search tree is the operation time complexity. So for example, if I am talking about insertion, or I am talking about deletion, or even I am talking about searching, the operation time complexity, what we say is order of log n, where log n is nothing but the height of that particular tree. Fine, that is a fact, but this log n time complexity can be only achieved if and only if your tree is balanced. Now imagine a tree, binary search tree, which is kind of skewed. So skewed in the sense, so for example, you have elements like 5, 4, 3, 2, 1. So 5 elements, and the height of the binary search tree is also 5, because all the elements are less than the root element. I am taking 5 as the root element. So here your tree, binary search tree, is not balanced. So what if, what kind of consequences it is going to face if it is not balanced? Then whatever we claiming as the kind of order log n time, that order log n time for the operations of search, insertion and deletion will not be kind of feasible if it is a skewed binary search tree. Or let me make it kind of more simple, that if it is a non-balanced tree, then binary search tree is not going to give you a time complexity of order log n. So basically, which scenario I am talking about? I am talking about insertion of a partially sorted data is kind of an optimally bad scenario for binary search trees. And so this was a background of binary search trees. Now looking into another data structure which is more kind of which is also used a lot, is linked list. So what are the benefits and drawbacks of linked list? So if you want to if it is a kind of a non-organized or non-sorted list, you can insert the element in order one time, and if you can if you want to delete a random element, that also you can do in order one time. And because this linked list is actually a dynamic memory structure, you don't need to estimate the total memory needed as you do in your arrays. So the two benefits with the linked list are easy to insert and deletion. I am taking it in order one time, and we don't need to assume, or we don't need to estimate the total memory needed. Fine. What are the drawbacks of this linked list? So let's say if you are trying to search a particular element, it is hard to search in less than order n time. So order n time will be required for searching, because I am not taking a scenario which is kind of a sorted list. So binary search is not going to work here unless your data structure is in a sorted form. And because binary search is not working here, and there are no indexes, it is a linked list which is connected with the help of pointers, so it is hard to jump in the middle also. Fine. So we have drawbacks and benefits both from the linked list, and we have also seen the scenario of binary search trees. What if I am going to combine the advantages of two? The advantages of two, that means I am trying to say that the search property from binary search trees I am going to take, and the kind of list structure I am going to take from the linked list, and I am going to combine the two, and the resultant data structure which I will be having is nothing but the skip list. So basically, what are the drawbacks which are available with your binary search trees and linked list? The skip list is going to fix those drawbacks. This is actually considered as a very good data structure for a dictionary. So any dictionary, if you want to implement as an abstract data type, I am not going into the exact implementation level details, hence I am saying it is a good data structure for a dictionary ADT. ADT here is in abstract data type. So let us begin with let us begin trying to understand this skip list. So skip list, this is basically a data structure which was invented around 1990 by Bill Pogue, and it is kind of, as I told you, it is a generalization of the linked list but in the sorted form, and hence it is so simple to implement. Search time as compared to a search time, unlike the normal linked list, is going to be order log n, but with a disclaimer that the search time which I am talking here is the expected search time. Now what is this expected search time? I'll tell you in a moment. Then this skip list is also considered as a randomized data structure. So this term randomized data structure is also very important. Why? Because when we are when we will be building this data structure, we will be using the random coin flips. So let us say coin flip is kind of resulting in head, then we are going to increase a level. If it is resulting in tail, then we will not be increasing a particular level or something. So basically this data structure is randomized because this randomization is using this coin flips to take an activity or to perform an activity. So skip lists are going to use some kind of randomization to maintain this order log n search and update time. And I have also told you earlier, and I am repeating it again, that these are expected figures, or I can say it in other words that these are on an average figures. When we talk about the detailed analysis of skip list, the worst case is going to be or I can say the worst rate could be potentially very bad, but on an average figures are going to be reasonably good, which are kind of order log n, and this order log n expected time for search and update are achieved with the help of randomization. Now what kind of randomization I am talking about, I'll let you know after understanding the structure of this skip list. So this skip list, by now you must have got the idea that this is kind of a linked list. So what kind of linked list I am talking about, you can have a look on the screen to just to have an idea. So this is actually a linked list in which there are different levels, and with different levels there are elements which are arranged in sorted order. So at the bottommost level, if you can see, it is having minus infinity as the header node, I can say, and plus infinity as the sentinel node, and in between whatever the elements are stored are actually stored in your sorted order. So you can see the elements, these are 12, 23, 26, then 31, 34, 44, 56, 64, 78, and so on and so forth. On the next level, it is kind of having some elements from the bottom level are repeated, not all. On an average, half of the elements I can say are repeated on the next level, and on the next level again the same procedure will follow, that almost half of the elements are repeated, and the topmost level is only having two elements, or I can say two nodes. One is minus infinity, which is the header, and another one is plus infinity, which is the kind of sentinel node, I can say. So, with this kind of a structure in mind, let us try to define this skip list in a formal manner. So, this skip list for a set S of distinct items, I am taking the items as kind of distinct, not unique, I can say. So, basically a skip list for a set S of distinct item is a series of list which is S0, S1, SH. So, basically I am saying S0 is the kind of I can say the lowest level, then S1 is the next level and S2 is the next level till SH, such that each list Si contains the special keys plus infinity and minus infinity, and each list S0 contains the keys of S in non-decreasing order. Now, coming back to this list again. So, this basically says S0 starts from minus infinity and set plus infinity, and it is containing a sorted list of elements. S1 the next level, S2 is the next level on top of S1, and S3 is on top of S2. So, in this way these kind of levels are arranged. So, I am assuming the level number starting from S0 to SH, where H is going to be the height of the skip list. So, the lowest level is having all the elements or all the keys arranged in an increasing order. The level just above the lowest level, which is S1 here, will be having some elements repeated. Now, what or which all elements will be repeated, that is that introduces randomization here, or the elements are selected by using the technique of randomization. Now, if I am talking about S2, so on S2 again on an average half of the elements of S1 are going to be repeated, and in this way these levels are being built. So, from the S0 is going to contain all the elements, S1 is containing half of S0, S2 is containing half of S1, all on an approximately half. I am not saying exactly half, but yes, approximately half, and your S0 is having minus infinity, or all the levels are having minus infinity as the the first node and plus infinity as the kind of I can say the last node. And each list is a subsequence of the previous one, as I told you. So, S0 is having less elements than S1, S1 is having less elements, more elements than S2. So, S0 is having the kind of largest number of elements and so on and so forth, and each list, which is S0, S1, S2, S3 contains only the topmost level SH will contain only the two special keys, which is minus infinity and plus infinity, and the skip list are one way to implement the dictionary abstract data type that I have already told you. So, this was actually the kind of list which we call as a skip list, and here you can have a kind of a I can say another version or a tweaked form of skip list. A skip list can also be maintained kind of like this. So, implementation level details may be kind of tweaked because this is an abstract data structure. So, please have a look at this figure which is available on the screen. So, left side we have the header nodes, and the rightmost side we have sentinel nodes, and we have nodes in between. And how this is being shown here is the element 2 is repeated at 3 levels, then your element 15 is repeated at the 2 levels, which I am assuming is S0 and S1. 16 is only available on the S0, while your 31 is available from S0 to S3, and your 96 is available from S0 to S1, and so on and so forth. So, this is also a kind of, I can say, way through which this skip list can be represented. So, if I say levels, so this S1, S0, S1, S2, S3, S4 are all the kind of levels, and the elements which are replicated on top of the top of each other. So, for example, let us say 38, which is replicated 4 times, or 12, which is replicated twice, and 84, which is replicated thrice. So, this is actually known as a tower. So, here we have a tower for 12, which is of kind of I can say 1 level, and here is a tower which is for 38 for 3 levels, and a tower which is for 84, which is for the 2 levels, and the element or the variable h, I can say, is nothing but height of a skip list. So, here the height of the skip list is 4, starting from S0 to S4, having different levels. So, in this way kind of we can visualize this structure skip list kind of a different flavor, or kind of, I can say, a different version of skip list is perfect skip list. Now, what is a perfect skip list? So, skip list says that the keys will be in the sorted order. So is in the perfect skip list, the keys are in sorted order. Number of levels will be kind of fixed, which is order log n levels. In case of a perfect skip list I am talking about, the number of levels is going to be order log n, and each higher level will contain half of the elements of the level below it, exactly kind of half of, or in case of an odd number, you can take a seal or floor, whatever, and header and sentinel nodes are in every level. So, with all these 4 properties in place, we can call a skip list as a perfect skip list. So, what are these 4 properties? One is very basic one, which talks about the keys to be placed in sorted order. That is what we have in this skip list also. Number of levels, order log n, and each higher level containing half of the elements of the level below it, and presence of header and sentinel nodes on every level is going to give kind of a flavor of perfect skip list. Now, the question which comes up in the mind, that let us say we are representing one particular element as a node. So, there are kind of pointers which are going forward. Then on a tower, there are pointers which are going on the above level, and there are pointers which are coming on the kind of the level below it. And apart from it, if I am talking about this as a doubly linked list, then there will be a pointer pointing towards the back node. So, what I am trying to establish is one particular node is having pointers in all the directions, that is top, bottom, or the above or below, I can say, and then left and right, which are forward and backward. So, what kind of implementation or what kind of node your skip list should have in order to kind of store all these elements. So, this kind of node we describe with the help of a term which is known as quad node. So, quad node, so skip list can be implemented. I am saying can be implemented because implementation, this skip list being an abstract data type, implementation details totally are totally dependent on the choice of the programmer, but we can implement a skip list with a quad node. Now, what is this quad node? So, for that you can have a look on the screen which is giving you a fair idea about the quad node. So, quad node stores what? So, quad node is having an item which is shown here with the help of the variable x. Then there is a link to the node before, that means the link which is going in the backward direction. Then we have link to the node after, which is kind of an a forward pointer. Then we have link to the node below, and then a link to the node above also is available. So, links to the node below and above are basically required to kind of I can say move around in towers. Now, why do we actually need to move around in towers? That we will see when we consider the first operation, that is the operation of searching. Also in implementation, we need to define the two special keys, as I have told you, which are header and the sentinel node containing plus infinity and minus infinity. So, we need to define the special keys plus infinity and minus infinity, and we will be modifying the key comparator to handle them, because minus infinity will be compared with a number, then plus infinity may also be compared with a number. So, in this situation, whatever your key modifier or sorry, the key comparator is there, that key comparator has to be kind of modified in order to take care of these special keys which are plus infinity and minus infinity. So, while going with the implementation, we need to be careful with all these details, that first we need a quad node which is having 4 pointers pointing in all the directions, top, below, forward, backward, and also a particular node item obviously will be there, and the important thing is the key comparator should be able to handle the special keys which are plus infinity and minus infinity. Now, in how are we going to use this these pointers which are pointing in different directions. So, for that we need to use some positional abstraction operations. What kind of positional abstraction operations I am talking about? One is after p. So, after p is a position after p on the same level. So, position after a particular element or after particular position p on the same level. Then we have before p. So, before p is a position before p on the same level. So, after and before are covered, then we are left with below and above. So, below p is position below p in the same tower, and above p is the position above p in the same tower. So, till this point in our lecture, what all we have covered is actually your what is a skip list, what is the background behind this skip list, or why this skip list is an important data structure, because your binary search trees and your linked list are having some of the drawbacks. So, skip list is trying to kind of skip list is trying to remove all these drawbacks and trying to combine the advantages of both the data structures, binary search tree and your linked list, giving you an expected operation time of order n. Then we try to understood that what actually this skip list is. That means how kind of this skip list is going to be is going to how you can imagine a skip list. Then we have seen the fundamental of levels and towers in a skip list, and from the implementation point of view, we have also seen that how to implement a particular node in the skip list, because this node is having pointers to all the directions as in kind of after and before, then below and above, because of the concept of towers and the concept of levels. So, level is a horizontal concept, tower is a vertical concept. So, in order to properly implement that, We also need to use a positional, we also need to use some positional abstraction operations which are after, before, below and above. So, in this way we have understood the basics of skip list which we started today, and we started with our new series which is advanced data structures and algorithms. And I hope you have enjoyed the lecture. We have covered the skip list introduction, and I will be soon seeing you in the next lecture with along with the operations of a skip list. I hope you must have enjoyed the lecture. Thank you for a patient hearing. I will see you in the next lecture. Till then, take care. Goodbye.